All right, welcome to 3.1. This is titled PES and Electron Configuration. PES will stand for photoelectron spectroscopy. So to define photoelectron spectroscopy, we're just going to simply call it the process of determining the amount of ionization energy required to pull an electron from an atom using different frequencies of energy. And if we want to take a look at how this is actually done, we're going to take a sample of material and we're going to shoot X-rays at it, or some other type of wavelength of energy. And when that energy hits the sample, electrons are going to pop off. Now, some electrons will pop off super easy. These are the electrons furthest away from the nucleus of the atom. And some of the electrons are going to require more intense X-rays, so they require more energy. These are the electrons that are close to the nucleus of the atom. Those electrons are picked up by a detector, and we can analyze exactly how many are coming off at a particular moment in time, and thus we can know exactly where those electrons are located. Again, the higher amount of energy needed to release the electron, the closer that electron was to the nucleus. So we talked about this process in class a little bit when we looked at these diagrams. These are called PES, or photoelectron spectroscopies. Now, there's a couple of things that we need to really clarify here. First of all, a PES has multiple scales. So if you start on the bottom of the PES, it looks like a traditional graph with 0 at the origin down here, and then the range actually gets larger as we move on to the right. But what happens is we look at all of the electrons inside of an atom. The range of energies that are required to remove the electrons are very widely. For instance, if you look down here on the bottom, you'll notice that some electrons come off with only 0.79 units of energy. So those electrons come off real easily. But on the other hand, the innermost electrons take 178 units of energy to come off. So if you imagine a scale where we had 178 right here and 0 here, that 0.79 value would be so minuscule, it'd be so small, it'd be so hard to see, it'd be way to the far left. And so what we do is we just divide our PES into 3 different scales: the small scale, the medium scale, and the large scale. Okay? What you have to remember when looking at these scales is whatever is on top, that's your core electron traditionally. Those are the electrons that are tightest or closest to the nucleus. They're the ones that are the most difficult to remove. So the tightest electrons require the most ionization energy. Right there, and that's those guys right there. All right, and then finally, the peak height represents the number of electrons in that subshell. So if you've got a really short peak, that might only be 2 electrons. But you can see as that peak grows, the peak is about 3 times the size as the 2 peak, means that there are more electrons in that subshell. Now, notice I'm saying subshell. We'll define that in a little bit. So what would this particular atom look like? Well, we have a total number of electrons in here that we can count. We've got 2, 4, 6, 8, and then another 6 is 14. So there's 14 electrons. And with a photoelectron spectroscopy, we're always going to assume we have a neutral atom. So this atom is going to be silicon, Si. So if we draw this particular atom, we know that there's a nucleus, and we know there are protons and neutrons in there, but right now we're only focused on the electrons. We know that there are going to be 2 electrons that are going to be located in the center of our particular atom, or in the closest to our atom, I should say, closest to our nucleus. So there those 2 are. The next shell is going to contain a total of, let's see if I can get a different color here. There we go. Okay, here we go. The next shell is going to contain a total of 8 electrons. Okay, so I got to place those 8 electrons right there. 5, 6, 7, 8. And traditionally they'd like to be as far apart from each other as possible. Okay. Once you reach 8 electrons in that next shell, you really can't put any more electrons there, so we have to go on to the next shell. And the next shell is going to be the outermost shell, which we'll define in a little bit. And as you'll notice, there's only 2 electrons in that outermost shell. So those 2 electrons go way out here. Those are my 2 blue electrons. Now if you think about which are the easiest electrons to remove, well, it's those last 2 that I put in. They're the furthest away from the nucleus, and remember that nucleus is very positively charged. And that makes sense when I look at my PES, because I notice that those blue electrons take a very small amount of energy in order to remove. And I said 2 electrons, but as you'll notice, it should actually be 4, right? There we go, 4 electrons. There it is, because we've got 4 total electrons in the blue box. So I've got 4 electrons that are in the outermost shell, and that's my valence shell. Okay, so that's a PES. And we'll get a little bit more to that subshell stuff in a little bit. That's important material. So what we can do now is we can essentially write the address for the electrons that are inside of an atom. And this address is known as an electron configuration, just simply defined as the distribution of electrons in atoms or ions. Again, we find this distribution by using the ionization energy and using the PES to give us a pictorial representation of that energy. Multiple peaks. Now I said before this word subshell. If, by chance, you have multiple peaks on one of your levels of your PES, like you do right there, that means that you have what's called a subshell in your shell. Okay, subshell in your shell. So all 8 of those electrons are relatively the same distance away from the nucleus. It just so happens that 2 of them are kind of hanging out in one subshell, and 6 of them are hanging out in a different subshell. Think about it this way. If you're in a hotel room, that hotel room has a particular number. Let's call it 318. So room 318 is room 318, but that might be a suite. So you might have like a kitchenette area and a bedroom area. So even though you are in room 318, there are 2 different rooms inside that room. And that's what the subshells really are. Now, we can use this concept to draw what's called the electron configuration for the silicon atom. So again, the 2 closest electrons, these are ones that are tightest to the nucleus. Let's define those first. Since they're in the first shell, the shell closest to the nucleus, they get a 1 in front of them. Now, the shape of that shell is the subshell. And every single time that we fit 2 electrons into a shell, we call that an S subshell. Again, we can fit 2 electrons in there, so we actually put a 2 exponent. That means that's the total number of electrons in that subshell. So it's the first energy level, it's an S subshell, and there are 2 electrons in there. So that covers that area. If we go down to the second area now, we are now in the second energy level. The first electrons that we need to account for are the ones with the highest energy. That's these guys right here. So those are in S because we can only fit 2 inside there. The next set of electrons we need to account for are the 6 that are up here. Once again, this is in the second energy level, but now since we can fit 6 electrons, we call this a P subshell. A P subshell can hold more electrons. How many in total? 6. Altogether, the red shell holds 8 electrons. Finally, if we come down to the third energy level, 3, we notice again that we've got 2 different peaks. That means there must be 2 different subshells. First one is always the S. It can hold 2 electrons. The second subshell, however, a P, can hold a maximum of 6 electrons, but the PES is showing us that it only has 2. And that means that it's not happy. Now, if you look at silicon, it's obviously not a noble gas if you check the periodic table, so it doesn't have a full outer shell. And so in this case, silicon is relatively reactive. It's going to do what it can to try to either gain or lose these 4 green outer electrons in order to become happy or stable. What we just wrote here, ladies and gentlemen, is called an electron configuration, and we're going to get plenty of practice with the electron configurations in class. All right. So if we take a look at silicon, if we look at this ionization chart and find silicon, it's the 14th element. And if we look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, there's silicon, okay? And it matches up with the atomic number that's below it. If we take any other elements, let's go ahead and take something small like lithium, for example. You'll notice that the ionization energy required to remove that outer lithium electron is very small, not a lot of energy at all. So how can we write the electron configuration for lithium? Well, it's got 3 total electrons. 2 of them are in the first subshell. The third one is in a new energy level in a new subshell. So that's the electron configuration for lithium. But we can also denote that using something called an orbital diagram. So what I'm going to do right now is going to be an example of an orbital diagram. Okay? So we've got a total of 3 electrons. The first 2 electrons are going to go in the first subshell, with the next electron going there in the second energy level in the S subshell. So that again is lithium. So both the configuration here and the orbital diagram here are examples of how we can track the electrons in the lithium atom. So just to recap, shells are the energy level of the electron. The outermost shell is going to actually equal the row the element is in. So for silicon, for example, that outermost shell was 3, and it's in the 3rd row in the periodic table. For lithium, the outermost energy level was 2, and that equates to the 2nd row in the periodic table. Subshells are smaller than shells. These are usually your SP and your D, the shapes of the shells. Again, we'll get into more of that practice in class. And finally, orbitals. Orbitals are those boxes that we showed on the previous page. The orbitals are the final resting place or the final room for the electron. So if you look at a periodic table, you can actually break down elements based upon their location. Any element over here is known as a P block element. If it's down in this row, it's known as a 3P element. Any element over here is known as an S block element. And if it's located here, it's known as a 4S element, because that would be the last configuration that we would draw. Just to give you an idea of an organization structure, the shell, again, is the outermost circular area that we usually imagine electrons rolling in. And then the subshells are the individual shapes. We got the circle and the peanuts. And the orbitals are the final rooms or the resting place for those electrons. Okay, so I'm nearing about 13 and a half minutes, and I don't want to do too many examples in class. I want to do a lot of examples in class, but let's just look at the electron configuration chart, which you can use for your practice, and do a small element, let's call it oxygen, and write the electron configuration for oxygen. So, oxygen, the first thing you want to check how many electrons, and we have 8 electrons. And now to follow the chart, you just follow your arrows. The first arrow goes through the 1s. Again, an S can hold 2 electrons. Then through the 2s, S subshell can hold 2 electrons. Now it's a total of 4 so far. And then you go to a 2p. 2p can hold 6 electrons, but if I had put 6 in, that's going to be a total of 10. So I can only put 4 electrons in here. So that is the electron configuration for oxygen. And you can use this diagram to help you. All right, that is 3.1.